Cooking is an art. That is what everybody tells you. Your grandmother told you. The fellow on television with the tall white hat, he tells you, you open a cookbook and right there on the first page it says The Art of French Cooking, Art. And you know, I believed it for a long time. I think most people believe it. You stand in the kitchen, you chop an onion, you toss it in the pan, it starts to sizzle and you think, well, this is creativity. This is feeling. This is intuition. That is completely wrong. And I am going to show you exactly why. I mean, think about how we talk about cooking. We say a chef has a feel for it. We say the secret ingredient is love. We say a dish needs soul. We watch these cooking competitions on television, and the judges close their eyes and chew slowly and say things like, this tells a story. A story. It is a piece of fish. What story is it telling? And look, I am not mocking anyone. I love good food. I have sat at tables where the meal was so good I did not want to talk, I just wanted to eat. But when people ask me why that meal was so good and the answer they expect is something about passion or tradition or the chef's grandmother's recipe, I have to stop them. Because the real answer is so much more interesting than that. See, when somebody says cooking is an art, what they really mean is, I do not understand what is happening. That is what art usually means. It means there is something going on that looks complicated, and rather than figure out the rules, we just wave our hands and say, well, it is a matter of taste, a matter of instinct. You either have the gift or you do not, and that is a perfectly respectable thing to say if you are talking about painting a landscape or writing a poem. But cooking is something else entirely, because every single thing that happens in your kitchen, every single thing, from the moment you turn on the stove to the moment you sit down and eat, is governed by physics. Not loosely governed, not metaphorically governed, precisely governed. The same laws that hold the planets in their orbits are deciding whether your steak is going to be tender or tough. And the funny part is, you already know this, you just have not realized you know it. Let me start with something everybody has done. You take an egg. A raw egg. You crack it into a pan. What do you see? You see this jiggly, translucent blob of goo. Clear, slimy, wobbly. You add heat. A few minutes later, that same stuff is white, firm, solid. You can pick it up with a fork. So what happened? Seriously, think about it. You did not add anything. You did not take anything away. You just made it hotter. And somehow it became a completely different material. Clear became white. Liquid became solid. How? If cooking were really an art, the answer would be something like, well, the egg expressed itself under the influence of heat. The cook's intention transformed the ingredient. That is nonsense. What actually happened is one of the most elegant pieces of physics you will ever see on a Tuesday morning. An egg white is made almost entirely of water. About 90% water. The rest is protein. And these proteins are not just floating around randomly. Each one is folded up into a very specific, very delicate three-dimensional shape. Imagine a long piece of string that somebody has wadded up into a tight little ball, but not randomly. Every fold is deliberate. Every curve is held in place by tiny electrical forces, attractions between different parts of the molecule. Hydrogen bonds, they call them, little hooks and latches made of nothing but the way electric charges pull on each other. When you heat that egg, you are shaking those molecules. You are adding energy, and as the temperature goes up, those little hooks start to snap. The folds come undone, the protein unravels. It goes from a tidy little ball to a long, tangled strand, and once it is unraveled, something wonderful happens. The strands bump into each other, and they stick, they tangle together into a mesh, a net, and that net traps all the water that was sloshing around before. Suddenly you have a solid white color. That is because the tangled mesh scatters light in every direction instead of letting it pass straight through. The same reason snow is white. Snow is just water too, but the crystals scatter the light. You did not perform art. You performed a phase transition driven by protein denaturation. You rearranged the molecular architecture of a biological material using thermal energy, and you did it in about 3 minutes while you were still half asleep. And here is the wonderful part. This same process has a temperature curve. Start at around 140 degrees Fahrenheit, 60 degrees Celsius, and the most delicate proteins in the egg white begin to unfold. By 155 degrees, the main proteins have locked into a soft, barely set gel. Push up to 180 degrees, and it becomes rubbery. Everything firms up. The water gets squeezed out of the mesh. That is why an overcooked egg is tough and dry and a gently cooked egg is silky and tender. It is not about talent, it is about temperature control. You are managing the degree of protein entanglement, and every degree Fahrenheit makes a difference. You can feel on your tongue. Now, people might say, fine, the egg is physics. But what about flavor? Surely flavor is where the art lives. The seasoning, the balance, the magic of a perfectly browned piece of meat. That must be intuition. No, absolutely not. Let me tell you about browning. You take a piece of meat, you put it in a screaming hot pan, and after a minute or two, something incredible happens. The surface turns brown, and this extraordinary smell fills the kitchen. Rich, complex, savory. There is nothing else quite like it. And for a long time, people called this caramelization. They figured the sugars in the meat were melting and turning brown like sugar in a candy recipe. But that is not what is happening. Not even close. What is actually happening was figured out by a French chemist named Louis-Camille Maillard back around 1912, and it is far more interesting than simple caramelization. What happens is this: the amino acids in the protein and the small amounts of sugar on the surface of the meat start reacting with each other, not melting. Reacting, they are forming entirely new chemical compounds, hundreds of them, maybe thousands, compounds that did not exist anywhere in the original piece of meat. New molecules forged in the heat of your pan that your nose and tongue have never encountered in that exact combination before. Each type of food produces a different set of these molecules, which is why brown bread smells completely different from brown steak, which smells completely different from browned onions. The starting amino acids and sugars are different, so the reaction products are different. This is not art. This is combinatorial chemistry happening on a cast iron surface. And it only occurs at temperatures above about 300 degrees Fahrenheit, which means roughly 150 degrees Celsius. Below that, nothing much happens. Above that, a cascade of reactions kicks off. The whole thing is a threshold phenomenon, like a dam breaking. You push and push and push. Nothing moves. Then suddenly everything changes at once. And this brings me to what I think is the single most important physics principle in all of cooking. It is so simple that nobody thinks about it, and so powerful that everything in the kitchen depends on it. Water boils at 212 degrees Fahrenheit, 100 degrees Celsius. And once it starts boiling, it stays at that temperature. You can crank the flame as high as you want. The water does not get hotter. It just boils faster. More steam, same temperature. This is a fundamental fact about phase transitions. When a substance is changing from one phase to another, from liquid to gas in this case, all the energy you add goes into the phase change itself, into ripping molecules away from each other, not into raising the temperature. Why does this matter for cooking? Because almost everything you cook is mostly water. Vegetables, meat, fruit, dough. It is all full of water, and that water acts as a governor, a speed limiter. As long as there is liquid water present inside your food, the interior temperature cannot exceed 212 degrees. The water absorbs the energy and converts itself to steam before the temperature can climb any higher. This is why boiled food and steamed food taste fundamentally different from roasted or fried food. When you boil something, the entire thing stays at or below 212 degrees. The Maillard reaction never happens because you never reach the threshold. But when you roast or fry, the surface dries out, the water leaves. And once the water is gone, there is nothing to hold the temperature back. The surface shoots past 300 degrees, the Maillard reaction ignites, and you get browning, crust, flavor, color, everything. So the difference between a pale, sad boiled potato and a crispy golden roasted potato is not a matter of art. It is a matter of whether the surface water escaped fast enough for the temperature to exceed the Maillard threshold. That is physics, pure and simple. Think about bread. You take dough, which is mostly water and flour and a little yeast. You put it in a hot oven. What happens? The inside stays moist and soft because it is full of water, and that water keeps the interior at or near 212 degrees. But the outside, exposed to oven air at 400 degrees or more, dries out rapidly. The surface temperature climbs past the Maillard threshold, and the crust forms. Brown, crunchy, fragrant. Meanwhile, just a few millimeters deeper, it is cool and moist. You have two completely different physical environments separated by less than a quarter inch of bread. Two different temperatures. Two different chemical regimes. coexisting inside the same dinner roll. That is not art. That is a thermal gradient doing exactly what thermal gradients do. Let me push this further. Consider a pot of soup. You have got water, vegetables, fat, maybe some cream. You stir it together, and it seems like one thing, one uniform liquid. But it is not. Fat and water do not mix. Everybody knows that. Oil floats on water. So how does a creamy soup stay creamy? How does mayonnaise hold together? Mayonnaise is mostly oil and a little bit of egg yolk and vinegar, which is mostly water. Oil and water. Mortal enemies. And yet there it is, sitting in a jar. Perfectly smooth, perfectly stable. The secret is emulsification. And it is beautiful physics. The egg yolk contains molecules called lecithins. And each lecithin molecule has a peculiar structure. One end of it loves water. It is attracted to water molecules. The other end hates water and is attracted to oil. So what does the molecule do? It sits right at the boundary between a tiny droplet of oil and the surrounding water. It parks itself at the interface with its water-loving end poking out into the water and its oil-loving end buried in the oil. It is like a diplomat standing at a border crossing, holding hands with both sides. If you coat enough tiny oil droplets with enough of these diplomat molecules, none of the oil droplets can find each other and merge back together. They are shielded, stabilized, and you get this smooth, creamy, uniform substance that looks like one thing but is actually billions of tiny oil droplets suspended in water, each one wrapped in a molecular peacekeeping force. That is an emulsion. That is what salad dressing is. That is what cream is. That is what a well-made sauce is. And if your mayonnaise breaks, if it separates into a greasy mess, that is not a failure of artistry. That is a failure of interfacial physics. You either added the oil too fast, overwhelming the supply of emulsifier molecules, or you let the temperature get too high or too low, destabilizing the interface. The fix is physics too. You start over with a fresh yolk, add the broken mixture slowly, and let the lecithins do their work one droplet at a time. I want to step back and look at all of this together. Because when you see it as a whole, something remarkable emerges. Every time you cook, you are performing an experiment in thermal physics. You are managing heat transfer, conduction through the bottom of the pan, convection in the swirling liquid, radiation from the glowing element. You are navigating phase transitions, ice to water to steam, solid butter to liquid butter to brown butter. You are triggering chemical reactions at precise temperature thresholds. You are engineering emulsions at the molecular scale. You are exploiting the fact that water has an unusually high specific heat capacity, which is why it takes so long to boil a pot of water, but also why water-rich foods cook gently and evenly. You are relying on osmosis when you salt your vegetables and draw the water out. You are using acid-base chemistry when you add a squeeze of lemon to brighten a dish. Let me stay on that salt point for a moment because it is a perfect example. When you sprinkle salt on a slice of eggplant before cooking it, within 10 or 15 minutes, little beads of moisture appear on the surface. The eggplant is sweating. People say the salt draws out the water. But what does that mean physically? The salt dissolves in the thin layer of moisture on the surface of the eggplant, creating a very concentrated salt solution. Now, inside the eggplant cells, there is a much less concentrated solution, and nature abhors an imbalance like that. Water molecules pass through the cell membranes from the dilute side to the concentrated side, trying to equalize the concentration. That is osmosis. The water is not being drawn by some mysterious force. The water molecules are simply doing what they always do, moving from where there are more of them to where there are fewer of them across a membrane that lets water through but holds the salt back. You exploit this process every time you salt a cucumber, brine a turkey, or cure a piece of salmon. It is physics, working at the scale of cell membranes, happening silently on your cutting board. A kitchen is not a studio, it is a laboratory. And the cook is not an artist. The cook is an experimental physicist who has not been told that is what they are. And you know what I find most wonderful about all of this? It is that the physics is what makes cooking reliable. The reason a recipe works the second time, the third time, the 100th time is not because of some mystical art being passed down through generations. It is because the laws of physics do not change. Water boils at the same temperature in your kitchen as it does in mine. Proteins denature the same way in Tokyo as they do in New York. The Maillard reaction does not care whether you are a trained chef or a college student making dinner for the first time. The chemistry responds to temperature and time. Period. That is actually the most profound thing about cooking. It is proof, daily proof, that the universe is lawful, that there are rules, that those rules are knowable. Every time you crack an egg and it turns white, the universe is telling you something. It is saying, I am consistent, I follow principles. And if you understand those principles, you can predict what I will do. Some people think science takes the wonder out of things. I think that is exactly backwards. Knowing that your dinner is a symphony of phase transitions and molecular rearrangements in interfacial chemistry does not make it less delicious. It makes it more astonishing. Because you are not just eating food, you are eating the laws of physics rearranged into something that tastes good. So the next time you are standing in your kitchen waiting for the water to boil, I want you to think about what is actually happening in that pot. Think about the molecules. Think about the energy. Think about the fact that you are holding a pan in your hand, and inside that pan you are orchestrating the same kinds of forces that operate inside stars, inside oceans, inside every physical process in the universe, just at a slightly lower temperature. Cooking is not an art. Cooking is physics. You can eat. Tell me something. What is the most ordinary thing in your kitchen that you now realize you do not actually understand? I want to know.